We are working on problem number 10 now. So in this scenario, we've got a block pulled along a rough horizontal surface by a factor F, by a force F, and it's applied at an angle. The block moves at a constant acceleration, and we want to express the results in terms of these constants. The first step says to draw and label a free body diagram showing all the forces acting on the block. And that's where you always want to start, whether it asks you to do that or not. So I'm going to start here. I've got a force downward of mg, and then I've got a normal force upward. I've got a applied force at an angle, and I've got a frictional force opposing the motion. When I am working with these type of forces, I wouldn't put my components in a force body diagram, although what I would want to do is draw the components here on the side. So I have a x component and a y component, and if this is theta, this is f cos, and then this is f sine. And then, of course, we've got our friction, we've got mg, we've got our normal force. Okay, so I did number A. It says for letter B, it says write an expression for the normal force applied by the surface to the block. The normal force is in the y direction, so I'm just going to do the sum of the forces in the y direction. Normal force is positive. The component of the applied force in the y direction is f sine theta in the positive direction and a negative mg. This is not accelerating, so I'm going to set that equal to 0. And then my normal force is equal to mg minus f sine theta. The next part, so this is for part B. Part C says to determine the coefficient of kinetic friction between the block and the surface. So our coefficient of kinetic friction, first of all, we're going to start with the fact that, and let me use a different color. For part C, we're going to start with the fact that friction is equal to mu k force normal, and that the normal force is mg minus f sine theta times my mu k. If we're going to determine the coefficient of kinetic friction, we're trying to solve for this mu k. And we know that there is an acceleration. I am just going to get rid of these graphs for now and use up that space to do some work, and then I can bring it back later. So first thing I'm going to do is I'm going to do the sum of the forces in the x direction. And so I've got my f cosine theta minus my force of friction, and that should say F for friction, which is mu k mg minus f sine theta, and it's moving at a constant acceleration. If I'm trying to solve for mu k, I need to isolate this. So I am going to actually add this expression to the right side and subtract ma to the left side. So I'm going to do a little swap there pretty quickly with algebra, and I'm going to get f cos theta minus ma is equal to m mu k mg minus f sine theta. And then I'm just going to divide the mg minus f sine theta over, so I get mu k is equal to f cos theta minus ma all over mg minus f sine theta. Okay, so for this next part it says, sketch two graphs on the axis below, velocity and displacement as functions of time, assuming the block started from rest and time equals 0. So if the block starts from rest, then we know the initial velocity is 0. And if the block starts at x equals 0 at time 0, I know my starting position in my xt graph is going to be 0. So the first thing we want to do is look at the fact that we have a constant acceleration, and this is a constant acceleration, which means that we're going to have a straight line as an acceleration. If the straight line is my acceleration, then my velocity has to be moving in a linear way. And if it's moving forward, starting from rest, then the velocity should be moving in the positive side of my axis in a straight line, increasing speed. And in that scenario, if I'm starting from the 0 position, then I want it to start at kind of a pretty slow speed and then increase speed exponentially. So that's what my position time graph is going to look like. This is constant acceleration, which we've been working with a lot last year and in the kinematics unit as well. So if they tell you it's constant, then we should have a linear velocity and then some sort of curve to our position time graph, and that v is supposed to be linear. All right, so for part E, this one I ended up dropping. Anytime you solved it, you would have ended up with MA equals MA, which really doesn't give you any valuable information if you're trying to solve for the acceleration value. So in the end, there's really no solution, at least that I could find for part E. So no solution. All right, good luck with this question and good luck on the test.